Okay, guys, as others of you are finishing up on the quiz, I want you to try number one, find the equation of tangent line. So everyone should have the test review packets.
Which one?
So first, you're gonna start off by finding the derivative, right? And the derivative, you gotta involve e to 2x and x squared rule, but the larger pieces, we gotta go through quotient rule, right? Quotient. So after you find the derivative using quotient rule, then you can use that x value to help you get to the order pair. That x value can also help you find the slope. Once you have your order pair and your slope, you can put that into point slope form and write your tangent line equation. We start off using quotient rule here. Okay, apply each term's derivative. F prime. Times G. Okay, so F prime G minus F G prime all over G squared. Let's do some cleanup. Okay, so we took care of the calculus and now we can go ahead and find our information for our point slope tangent line. So -1 into the function will get us our y value. So we have our order pair. We can also find our slope. Slope comes from the derivative, so we can just take the -1, insert into y prime. All right, do some cleanup. The -1's squared and to the 4th will go away. So this will just go away to 1, so I'm left with 2 over e squared plus 2 over e squared, which is 4 over e squared. Okay, so we have our ordered pair, we have our slope, and now point slope form. Okay, tangent line equation. These are problems that we've learned, we've been working on ever since we started unit 2 with derivatives, but we'll see this on the test as well. Okay, so every time we learn a new derivative rule, we're always going to find the equation with tangent line. But the process is the same. You find the derivative and use the x value to get your ordered pair. Use the x value to find your slope, and then point slope. So you see something like this on the test. Any questions with this? We did a curve sketching problem on Friday. We're gonna do another curve sketching problem later on, but I just want to let you know that with curve sketching, I'm only going to be asking for relative interval increase, decrease, relative max, relative min, POI, concave up, concave down, but I'm not going to ask you to sketch the graph. Okay, so on the test, you just have to gather the information, use your sign line, you write your because statements, just like very similar to how you did on the previous test, but just with a new set of derivative rules to apply, but same process, and no sketching graphs. Okay, so let's skip this problem for now. We just did this on Friday. We'll definitely revisit it over the course. There's a couple more problems like this in the packet, but let's go to page 2. So you'll see extend the problem involving curve sketching, which is everything I just listed. You'll see equation of tangent line, and then you're also going to see particle motion problem. We're going to do a couple particle motion problem over the course of these next days, but let's start with this one here. Particle motion is basically finding the first derivative, setting the derivative equal to 0. Basically, a first derivative sign line. It's just that instead of a positive slope, now a positive means moving to the right. Instead of a negative slope, now negative means moving left. And then instead of a relative max, relative min, now change in sign means that the object is motionless in terms of its velocity. Okay, we also call this PVA. PVA representing position, velocity, acceleration. That relationship between function, first derivative, and second derivative. So let's read this problem here. A particle moves along the x-axis so that at any time t greater than 0, its velocity is given by v of t. Okay, now normally we see problems where you're given the position, and then you have to find the first derivative to get to velocity, and then the second derivative to get to acceleration. But here, the problem already gives you velocity, so we can go from velocity to acceleration, but we don't yet know how to go from velocity back up to position. Okay. We'll learn that second semester when we're kind of working backwards through our antiderivative process. But here, it's already given to you velocity, so we can don't have to find the derivative to get the velocity is already given to us. Okay, so part A says write an expression for the acceleration of the particle. So what process do we need to get from velocity to acceleration? Derivative, right? First derivative. So let's look at this function in detail here. Let me write this out again. All right, what process is involved here if I do want to find the derivative? Product rate, right? T and natural log of t, those are clearly two separate terms, but they're being multiplied. You got to go through product rule, and then within product rule, we can handle each individual rule. All right, FG prime. Okay, so f prime, t becomes 1. Keep the natural log. Back to f. Okay, g prime, natural log of t becomes what's 1 over t, right? U prime over u. So all that takes care of my t, ln t. I still got to worry about that minus t. So minus t becomes minus 1. Okay. All right, so t over t becomes 1. 1 minus 1 is 0. So my acceleration is just natural log of t. All right, so we took care of part A. We have our acceleration function. Part B, for what value of t is the particle moving to the right? So we're back to using what function to get all this information? Yeah, the velocity, right? So we got to do some things with the velocity here. So before we can decide whether it's moving right, we first have to do what? Set velocity equal to 0. Yep, we're going to find the critical points, create our velocity sign line, create intervals, test each interval, and then assign each interval with a plus or minus. All right, so I set velocity equal to 0, 0 equals t ln t minus t. Algebraically, how would you get to the point where you can solve for t? What can we do? Factor, right? GCF is t, so that means I'm dividing t from both these terms. So if I divide this first term by t, I'm left with natural log of t. If I divide t by t, I get 1. Yeah, so okay. I got factor form. Set both parts equal to 0. So t equals 0, that's already done. So we can set that off to the side. Natural log of t minus 1 equals 0. I'm going to get that natural log of t by itself. So there's two ways that we can arrive at this t-value. We can think about what the graph looks like and kind of go through it that way. Okay, so if you think about your natural log graph, natural log of what gives us 1? Natural log of e gives us 1, right? So if you think about, yeah. So if you think about your natural log graph, natural log of e is equal to 1. So it's good to memorize this graph, but we can also do this algebraically, right? Because we didn't know that off the top of your head. You can also work it out. Raise both sides with e as the base. We know e and natural log are going to have a way of kind of canceling each other out. E and natural log goes away. The t drops down. T equals e to the first power. Anything to the first power is just going to be that base, right? T equals e. Okay, just a heads up, no calculators on Tuesday's test. Okay, no calculators. All right, so we can create our velocity sign line. 0, even if 0 wasn't found as the critical point or as a t equal 0, we're still going to include 0 because it says time greater than 0. So 0 is a starting point, no negative numbers, so that kind of creates a given boundary for us. All right, we want to test each interval with values. So what an easy value we can choose between 0 and e1. Okay. And then to the right of e, I can choose. Yeah, so 3 is fine. Also, e squared is fine. I like e squared better, but I'll work through it both ways to kind of show you that you can still arrive at the same conclusion. All right, we're going to plug 1 into the velocity function. I like the factored form. Kind of gives us, we don't have to do as much calculation. We can just kind of combine all the signs and see whether we get positive or negative. So let's plug 1 in first. So 1 in for t, that's positive. Plug 1 in for t. Natural log of 1 is what? 0, right? 0 minus 1 is negative. Positive times negative is negative. So I know my interval is negative. So it's moving left in that first interval. Okay, I can choose e squared or 3. Let me plug in using e squared here. So I get e squared times natural log of e squared minus 1. Right, the nice thing with natural log of e squared, they're going to cancel each other out. This just drops down to be 2. So e squared is positive, and then 2 minus 1 is also positive. So positive times positive is positive. If you want to work it out using 3, that also works. If I do 3 parentheses natural log of 3 minus 1. 3 is positive, natural log of 3. So natural log of 3, go to your graph here. Natural log of 3 is to the right of e, so somewhere here. So give me a decimal value. 1.2, 1.1. We know it's greater than 1. So let's say 1.1. So 1.1 minus 1, that is still positive. So we still get that same result. So moving left stops at t equals e, and then starts moving to the right. So for what value is the particle moving to the right? So moving right from e to infinity. Again, whatever value you test is not part of any other part of the problem. Okay, the whole point of the 1 in e squared is to get the signs to show up. After that, we don't have a use for it. And the reasoning is because velocity is what? Greater than 0. Yeah. Okay, part C. What is the minimum velocity of the particle? Show the analysis that leads to your conclusion. So I want to kind of give a visual connection with part C here. Okay, minimum velocity. Okay, what would that look like? Well, let's say we're looking at the velocity graph. Okay, and velocity. Let's say the velocity graph looked like this. Okay. We can tell that is the minimum, right? But if this is a derivative graph, okay, velocity graph, the same thing as derivative graph, f prime, right? If you saw a valley or minimum of an f prime graph, what does that mean to you from an original function standpoint? UI, that's point of inflection, right? The peaks and valleys of your derivative graph is the point of inflection of your original graph. So the minimum velocity is going to occur where there is a point of inflection, right? And the point of inflection specifically
if you were to create a second derivative sine line, minimum velocity is going to occur if that critical value, let's say it was, let's call that A here, if it is followed with a concave what? Yeah, that's right. So we're not looking at the shape here, we're looking at the slope. Negative slope is concave down, followed by concave up. So if I can get this property to show up with my second derivative sine line, I know that that point of reflection is also the minimum velocity, right? Minimum of your f prime graph, we're just replacing f prime with velocity. So let's go ahead and find our second derivative function. Well, we already did, right? Acceleration, which is natural log of t. So we just go through the process, trying to find that where acceleration is equal to 0, and then create our second derivative sine line. So a of t equals natural log of t. Replace a of t with 0 because I want to look for critical points. 0 equals natural log of t. For what value of t is natural log equal to 0? 1, right? Natural log of 1 is 0. So we can do that based off of the graph, but we can also do this algebraically. Raise both sides with e as the base. E to the 0 power is 1. E in natural log goes away, so t equals 1. So here's my acceleration sine line. We want to test our intervals against the second derivative function or against the acceleration function. What can I choose between 0 and 1 half? 0 and 1. 1 half. And then to the right of 1, I can choose 2, but maybe what could be easier? E, right? But 2 is fine. You know, we can still get to where we want to get to. But anytime I can take advantage of E, especially with natural log, I know things will work out easy. Okay, so natural log of 1 half. What's natural log of 1 half? Somewhere here, right? Which is negative, right? So negative, I know second derivative there, concave down. E, if I plug E in here, natural log of E is 1, that's positive. So there we have it, right? We have this property going, right? If this is a velocity function, the velocity function will be decreasing to represent concave down. It's the point of inflection rises. So this is minimum velocity. Okay, let me see if I can squeeze in number 4 here. Number 4, I want to find the derivative, y ln of x plus y squared equals 0. What process do we have to go through if I want to find the derivative? If it's in this form. Good, implicit, right? Anytime you see y's mixed into the equation, you know you got to collect your dy dx's. What else? Product rule, good. Now, we're not seeing it in this problem, but we're going to see it in future problems. Is you also want to consider if there's logs involved, is there an expansion that we can do with logs? So let's say it was like natural log of xy. Let's say natural log of xy was somewhere in this problem, then you would make that natural log of xy look like what first? Natural log of x plus natural log of y, right? It just makes your process a little bit easier. So I know it doesn't occur in this problem, but just want to bring up those 3 things that we're going to see those 3 things kind of mesh together in future problems. But at least we do see implicit and product rule. We see product rule built into this first 2 terms there, y and natural log of x. We got to go through product rule. Okay, so let's go through our derivative here. Y becomes dy dx, good. The original g function, no changes, natural log of x plus f function back to y, okay, g prime. What's natural log of x become? 1 over x. Okay, so we took care of that product term there. Plus, we got to finish out the rest of the equation. Y squared becomes 2y. Good, 2y, but we just took y's derivative. I need to collect my dy dx there. Equals 0. Okay. All right, so my calculus is done. Now I can just try to collect my dy dx's here. I'll merge the y over x together as a fraction, move it over to the other side, make it negative y over x. Factor out the dy dx. And then divide the fraction or divide the parentheses over. But I got a fraction on the right side, so dividing by parentheses is the same thing as multiplying by its reciprocal. And that way I can get it to look a little cleaner there. We didn't get number 5, but we'll start with that tomorrow. Okay.
All right, don't forget your phone.
I remember it. I not remember it. I mean, yeah, I remember.